Hi guys, welcome back to Data Every Day. Today we are looking at a data set of audit data for firms. So these are firms that were audited, and we're trying to classify if a given firm is fraudulent based on the present and historical risk factors. So we have a bunch of features about the risk of a certain firm, and we're trying to predict if it's fraudulent or not, which is given by this final column, which is the risk column. 1 meaning it's fraudulent, 0 meaning it's not. So I'm not sure exactly how the audit risk and risk are related, because I did notice when we were doing this that the audit risk has a tremendous impact on the risk. Like some of the models tend to use only this feature to make predictions. So I'm not sure. There's not too much information about it, but I'm just going to use all the features and then try to predict risk with it. So let's hop into the notebook. We're using NumPy and Pandas for working with the data. For pre-processing, we'll be using the train test split function and standard scalar from sklearn. And we'll do a whole bunch of models today: logistic regression, k-nearest neighbors, decision tree, support vector machines, a neural network, and then we'll just use two ensemble methods, random forest and gradient boosting, which are both tree-based. Let's go ahead and import all of that, and we'll start by loading in the data with pandas.read.csv. And we can grab the file path to the CSV file right here in auditdata.csv, paste that in, and we can take a look. So we have 27 features and only 700 rows, 776 rows. Not too bad though, we can still do something with this. And you'll notice everything is numeric. The only column here that we do have to encode is the location ID. So although this looks numeric, I believe it's actually a string column. You can see here is object if we do data.info. And I think there's like 2 text values in here. But even if it was all numeric, these are unique values that correspond to IDs. So we are going to want to one-hot encode this. Now, whether you want to leave this column on or not is up to you, because it's important to think about what this model would be used for in production. Now, I'm not entirely sure what location ID says. It says unique ID of the city and province. So if we keep this on, our model will sort of rely on this kind of information to make predictions. So if we wanted to make a prediction for a new firm that was in a state or province not listed in the original location ID column, then this column would be basically useless for making the prediction, because we'd have to put in some new value that the model wouldn't know what to do with. So if we were trying to build a model that was could make predictions regardless of what location we were dealing with what city or state we're dealing with, we would want to drop this column. But if we're pretty sure that all the firms are going to lie in one of the values listed in this column, then we'll keep it on. And I guess we'll keep it on for today. So let's hop into the pre-processing section. I should also point out we have, I think, one missing value in this whole data set right here. We have a single missing value in the money value column. So we're going to have to fill that in. I'm going to create a function called pre-process inputs. It's going to take in a data frame, and it's going to make a copy, which we will do all of our pre-processing on. So I'll return just the copy, and for now all this does is duplicate the data set. So pass in data, get back x, and x is the copy we'll do our transformations to. So I guess there's really only 2 steps for this case. One would be to one-hot encode the location ID, and the other would be to fill in the missing value in the money value column. So let's do the missing value first. So fill missing value. There's only one. df sub money value equals df sub money value dot fill na. So we just pass in what we want to fill the missing value with, and since it is a numerical column, why don't we fill with the mean of the column? So we'll do df sub money value dot mean. And now if we run this, well, before if we run it, we check the is_na matrix and sum across the rows. We'll see that there's a single missing value in the money value column, zeros in all the others. If we now run this, and then take a look, you should see this 1 should turn to 0. And there we go, it's now 0. So we're done with missing values. and now we'll do the one-hot encoding. We're going to one-hot encode the location ID column. So for one-hot encoding, we're going to take the column, which looks like this, and use pandas.getDummies to send each unique location to its own column. You can see there are 3 text values in there. And a 1 in a given location will correspond to the original value of that example. So you can see the first 3 examples it has a 1 for 23, a 1 for 6, and a 1 for 6. And that's because if we look up here, the first 3 examples have 23, 6, and 6. So I'll also point out that we can include a prefix here. Why don't we call it location? And that will just put location at the beginning of each column name so that we know where these values are originally coming from. So let's use this up here. Instead of x, we're using df. And let's call these location dummies. So once we have these location dummies, we're going to put it onto the original data frame. So df equals pandas.concat. And we're concatenating the original data frame and the new location dummies side by side, so axis 1. And then once we add them together, we can drop the original location ID column, since we've extracted all the data we want from it. So here's x now. The original location ID column is gone, and we now have all these locations, which are the one-hot columns, all for every single unique value in the original column. So now we now have 71 features, or 70 features, and a single risk, risk column. And so this is what we're trying to predict. So let's split it. Let's split df into x and y, where y is what we're trying to predict. X is all the rest of the data. So we're dropping it from axis 1, storing that in x, and then we'll do our train test split. So we want to send some portion of the data to the train set and the rest to the test set. For this, we can use the train test split function from sklearn. We just pass in x and y, specify how much we want to send to the train set. Why don't we do 70%? Keep shuffle equals true, so this will shuffle the data set before it makes the split. And because it's shuffling, let's use a random state so we can reproduce the results. Now this will return 4 new sets of the data, which is xtrain, xtest, ytrain, and ytest. And those are the sets of the data I want to return from this function. So we'll get them back over here, and let's take a look at xtrain. So we have lost a column. That's because the risk column is now stored in ytrain, which is just a single label column. And we also are dealing with 70% of the original data. You'll see that the indices have been shuffled because of the shuffle equals true, but the y indices match up to the x indices. Alright, so the last thing to do would be to scale the data. The means and variances, well, I'll just say the range of values that each of these columns take on are very different. Some of them are just zeros and ones. Others you can see are into the tens. So we do want to standardize them in some way. So there's a few ways to do that. We'll use a standard scaler. Scale x with a standard scaler. So our scaler is a standard scaler from sklearn. And the standard scaler will shift and scale each column so that every column has a mean of 0 and a variance of 1. So we're going to fit the scaler just to the train set. So we're going to calculate how much to shift and scale by just by looking at the train set. And then we're going to actually shift and scale using that calculation for both the train and test set. So we can do that with scalar.transform and store that back in xtrain. And the reason we only fit to the train set is because we want to pretend we don't have access to the test set when we're doing this scaling. So this actually returns a NumPy array. So if I were to run this, it has been scaled, but we can't see it as a nice data frame anymore. So let's turn it back into a data frame. And we want to make sure to keep the indices the same as they were, and the columns the same as they were, the column names. Then we'll just copy this whole thing over and do exactly the same thing for xtest. Alright, there's xtrain, and you can see it's all been scaled. So if we were to look at the mean of every column. You can see they all have means of 0, or very close to 0, and the variances are all 1. This 0 variance, you don't have to worry about it. That's just because there's only one value in the column, and that's because of the one-hot encoding. If you one-hot encode a single a single occurrence, and that occurrence happens to end up in the test set, then when you fit to the train set, you're not going to see more than one value. So this has a variance of 0. But that's okay. Alright, so I think we're ready to train. So training. We're going to do a whole bunch of models. So let me just paste in this dictionary for the sake of time. This is mapping the name of the model to the instance of the model. And we'll fit the instances and use the names to display some messages about them. So we can iterate through for name and model in models.items. And models.items allows us to get the key value pairs as tuples, so we can iterate through 2 at a time. And we'll just fit each model to the train set. So xtrain, ytrain. And we'll print out a little message that says the name of the model and that it was trained. Alright, so it's training the models. It's finished. And let's get the results. So again, we'll iterate through for name and model in models.items. And we will here just print out a little message that takes the name of the model and displays the accuracy value for a given model. So these are classification models, so we can get the accuracy value using the model.score function. So let's display it to 2 decimal places as a percentage and format that with model.score of xtest and ytest. And I'm going to multiply it by 100 since we're doing it as a percent. Alright, and there we go. So we can see we're getting really good results. So whenever you get really good results like this, especially if you're seeing 100%, you got to be a little suspicious. Now I can't be sure because there's not so much information given about the dataset. It doesn't have detailed descriptions of each column. Like for example, the audit risk says total risk score using analytical procedure. And then this one is risk class assigned to an audit case. So it's possible that the risk target value is a function of the audit risk, in which case we should drop the audit risk. We don't want to. It's hard. It's hard to say. You got to think about what the model is doing in production. So what features would we actually have available to us at the time of a new training example? So let's say we have a new firm and we've analyzed it. Will we have audit risk available to us at that time? If so, then it's a valid feature and we can definitely use it to predict whether it's a fraudulent firm. But all these other risks, detection risk, inherent risk, control risk, risk F, there's a whole bunch of risks in here. And we just want to make sure, I can't verify this, but you would want to make sure which of these you actually have available to you when you want to use the model to predict on new data. So I can't be sure which of these columns would be available to us, but you can see that when we do have them all, we actually are getting very, very good results, especially the tree-based models. All 3 of our tree-based models are getting 100% accuracy. Everything else, aside from the tree-based models, are falling shortly behind, the lowest being a 90% with the k-nearest neighbors algorithm. Alright, and that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.